Hello everybody, this is Professor Algara and welcome to our new video. We are going to keep working on chapter number 3, properties of pure substances. We were talking about the different states that the thermodynamic dome will have, and we were just developing the diagrams in thermodynamics. I plan on finishing chapter number 3 today. I will explain you how to use water tables and ideal gases equations and things like that. So let's just get started.
There are two terms that need to be developed, okay, before we get into the tables. Saturation temperature and saturation pressure. Those two, okay? Saturation temperature and saturation pressure, okay? How do we define those terms? Temperature is the temperature at which a pure substance will change phases at a given pressure. Saturation pressure is the pressure at which a pure substance will change phases at a given temperature. Pretty much, if you want to make it simpler, when you have saturation, okay, that single word will pretty much means change of phases. Okay? If you have saturation temperature, is the temperature at which a pure substance will change phase at a given pressure. If now I go with saturation pressure, is the pressure at which a pure substance will change at a given temperature. Let's say, for example, going back to this little drawing, I have my diagram, which is dV. That saturation, it's this one right here. Why is that? At this temperature, my substance is changing from liquid to vapor. And that's why this guy right here is called the saturation temperature. Will be the temperature at which it will change phases. Okay? What happens before or with a lower temperature? Let's say something here. Then when you go like this, you're gonna hit only liquid. So it's only one phase. And what happened after that? Let's say here, if I keep moving like this, then I reach superheated vapor. It's only vapor. So that temperature, 100, in this case particularly, it's called the saturation temperature. Okay? It's a temperature at which this substance will change phases. And then we have, the diagrams in which we're going to have different information. And I want to just go over the information one more time. And I think I've repeated this probably like 3 times. But anyways, we have saturated liquid line. Is this one right here. And this line is pretty much the limit between liquid and mixture. Right? And then we have something that is called saturated vapor line, which is pretty much on the other side of the critical point. In this side of the diagram per se, I will have the limits between mixture and vapor. And then we have something, or we start defining the regions. We have the compressed liquid region, which is this one right here. And that compressed liquid region, I only have liquid, like I said. Okay, regardless of the pressure or the temperature, I only have liquid in that state. Then we have another region, which is saturated liquid vapor region. In that region, I have liquid and vapor both combined. I will have different amount of liquid on this point than I will have on this side. As you move from here to here, liquid will start disappearing and then more vapor will be created. And then we have the last region, which is superheated vapor region, and that region pretty much is the region in which we have only vapor. Okay, so I want to recap everything. And again, this is in the book, it's more explained in the book, but I want to show you something. I have 2 diagrams. I have the T specific volume diagram, and I have pressure specific volume diagram. How do they work? I have the first one. zone, and this one goes like this. I have a specific volume on this end and temperature on the other end, and temperature on this end. This line right here, it's line of pressures, different pressures. You're going to have different lines, because the pressure will go up, and that will depend. Then we have something here that we don't really care about, and that's called the critical point. What happened at the critical point, I'm going to just explain it to you, but don't worry. Okay, and then we have, let's just stick with this line right here, the one in the middle. This one will have 2 points. This point right here, it's called VF, and this one is VG. Okay, right here I have compressed liquid, that's the stage. This stage is mixture, and then I have superheated vapor. This F right here is for fluid, and this one is for gas. Okay, remember what happened on these 2 points. And BF is the last, or I'm gonna say the limit between liquid and vapor. Okay, as you move through this area, you're gonna have more liquid than vapor, more liquid than vapor, more liquid than vapor, and as you approach to the other side, it'll be more vapor than liquid, more vapor than liquid, until you reach that end right here. And we have the point, which is a specific volume related to the gas. Okay, just put a pin on it because we're going to use that in a little bit. I have the other one. It's called PV, and this one has a little different behavior. These lines will be temperature lines. These lines are on the other side, these ones are pressure lines. Okay? These points, I'm just going to focus in the middle. The same thing, compressed liquid on this phase, mixture on this phase, and superheated vapor on the other phase. I have 2 points related to this, which is this and this. And this point will be called BF and BG. And they will mean exactly the same thing, fluid and gas. What happened with these two? You could also have a specific volume. You could have something that is called enthalpy, and we're going to define it in a little bit. We could have, internal energy. We could have the same thing here, enthalpy and internal energy. Please save this, put a pin on it. Once you read the book, it will make sense, okay? That's how you express the behavior, thermodynamically speaking, of a process. Okay, you'll see how it's like once we move into the following chapters. What happened at the critical point? Super simple. It's the point at which the saturated liquid and saturated vapor states are identical. That's pretty much the definition. And I will completely honest with you, just keep that definition. That's what's really important. Anything after that is not really important. And we reach something that is called property tables. Okay, for most substances, the relations among thermodynamics properties are too complex to be expressed by simple equations. Therefore, properties are frequently presented in the form of tables. Some thermodynamic properties can be measured easily, but others cannot and are calculated by using the relations between them and measurable properties. The result of these measurements and calculations are presented in tables in a convenient format. So, our property tables, if you think about it, it's a way in which we're going to see how water, in this case, will behave at different temperatures. So for each one of these temperatures, you're going to have a value of pressure, a value of enthalpy, a value of entropy, internal energy, and so on and so forth. Okay? Just remember that. And we're gonna define a property. Okay, property like this one will be found in chapter number 7, which is entropy. But enthalpy, it's a combination property. Pretty much, it's a combination of the internal energy plus the energy that the fluid will carry. When you have pressure times volumes, yeah, that would be a form of energy. The combination is usually, or I would say often encountered in the analysis of control volume. Okay, so like I said, enthalpy, it's another property like it was internal energy. That is, it's another form of energy that will combine internal energy and the energy carried by the fluid. So saturated liquid and saturated vapor states. What happened in these ones? Let me just go back to this. Saturated liquid, saturated vapor, saturated liquid, and saturated vapor. We need to do something about it because why is that? A compressed liquid, the properties can be found very easily, okay? Because everything is liquid, and we have a property table that has just okay, but at a given temperature, then you will have enthalpy, internal energy, entropy, etc. And then the same thing will happen with superheated vapor. But when you're in mixture, you don't know exactly how much water or how much vapor you have. That's why the mixture one, it's one of the most complex ones because you need to calculate some things in order to define that state. So let me just start explaining. Okay, BF, like I said, is a specific volume of saturated liquid. BG, it's a specific volume of saturated vapor. VFG is the difference between VG and VF. That is pretty much as VG minus VF right here. When you are in the mixture tables, you're going to have a temperature, a saturation pressure. Remember the pressure at which, the substance will change phases. Along with this, you have a VF and a VG. And why is this important? This is important because we need to know exactly how much gas or how much liquid I have in my mixture. So we're going to define something that is called quality X. So quality X is pretty much the ratio of the mass of vapor to the total mass of the mixture. Quality will be between 0 and 1. Okay, remember that quality will go between 0 and 1. How do I calculate quality? Pretty simple. So you will be given with the amount of vapor that you have and also the amount of the whole mixture that you have. If you divide the mass of the vapor by the total mass, then you will get quality. And quality is just a number. It doesn't have any unit. Okay, it's unitless. Okay, and the quality will be the one that will tell you exactly how much gas or how much vapor or how much liquid you have. Quality will go from 0 to 1. Okay, so at VF, quality it's equals to 0. At VG, quality it's equals to 1. Guys, remember this because it's very important. And this value will go from 0 to 1. Okay? How do I calculate the total mass? It's mass of the liquid plus mass of the vapor. Okay? That's good to know. Like I said, guys, you need to read the book. Okay? It's very important. It's impossible that with my explanation it'll make sense. You need to go on your own and read the book. What happened? Okay, how do I calculate with all this information that you're giving me? How do I calculate for example, if I'm looking for a specific volume, how do I calculate a specific volume with BF, BG, or BFG, and also with quality? How do I calculate that? It's kind of, a little hard to calculate or pretty much, tell you an equation and just throw the equation like this. So because I don't want to do that, I'm going to play a little bit with the equations. Okay, so pay attention to this. I know that my specific volume, it's equals to BF plus BG. We know that, right? We also know that volume, regular volume, it's equals to the mass that multiplies to the specific volume. Okay, we know that from chapter number 1. We were giving in the previous slide that my total mass it's equals to mf, which is fluid, plus mass of the gas. Okay, we know that. We also know, and very much think about it, I'm gonna play with this equation and that equation. Yes. All right. So how do I play with this? Okay, sorry. So how do I play with these equations? It is simple, guys. So I'm gonna play with the equation that I have right here, like I said, and I'm gonna go like this. My total mass times an average specific volume will be equals to mass of the fluid times the specific volume of the fluid plus mass of the gas times a specific volume of the gas. And I'm gonna call this guy right here equation number 2. You know what? Equation number 1. Okay? What other equation do I need? Okay, I'm gonna grab this equation that I wrote on top, and I'm gonna solve this equation for mass of the fluid. Mass of the fluid, it's equals to total mass plus mass of the gas. And I'm gonna call this equation number 2. And I'm gonna take 2 into 1. Okay? How do I do that? Well, I'm gonna have mass total times B average, it's equals to mass total minus mg BF plus mg BG. Okay, what did I do? I just took this equation and plug it into this guy. Okay, I hope there's no questions. What I need to do right now is solve for my V average, because that's what I'm looking for. If I solve for V average, I will get something like this. MT minus mg times BF that multiplies MT plus mg over MT that multiplies BG. And that's another equation. So I hope everybody's following me. So what else can I do in order to develop this equation a little further? And this is what I'm gonna do. I'm gonna remember that quantity, somebody told me in the past that quantity is equals to the mass of vapor over total mass. Okay? What else do I know from the past? Somebody told me that BFG is equals to BG minus BF. Okay? And I'm gonna use these two guys right here in order to simplify my equation a little more. Okay, MT, MG, and I have MG, MT. Okay, how do I simplify this? So B average will be equals to 1 minus X that multiplies BF plus X that multiply BFG. And this guy, it's the equation I need in order to calculate my specific volume. Let's say, and again I'm just giving you one equation, but the real question would be, no, I'm sorry, I made a mistake. Wait a minute. Okay, just go back. Sorry. Okay, plus
x Bg. Okay, so I need to develop this equation a little bit more. Bf minus x Bf plus x Bg. Okay, cool, that's fine. This is a little bit more like Bf plus x that multiply Bg minus Bf. And if I keep developing this a little bit more, okay, I'm just going to delete this guy a little bit. Okay, I hope you copy. Okay, so if I keep developing or simplifying my equation, I will get that V average it's equals to Vf plus x Bfg. Perfect. So that's the equation I was looking for. Sorry for before. Alright, so that's the equation I was looking for. Just 1 second, this guy. Let me keep this. That's the equation I was looking for, because when you have Vg, Vf, and Vfg, and you need to calculate your specific volume, you need to have an equation in hand that you can use. Okay, for sure you need more data. You need to know the total mass, you need to know the mass of the vapor, you need to know a lot of things in order to develop this equation. But at the end of the day, this is the equation I need, and I'm gonna rewrite this equation. A specific volume, it's equals to Bf plus quantity Bfg, and that will work for internal energy too. Uf plus x Ufg, and it'll work the same thing for enthalpy. Hf plus x Hfg. These are the equations, guys, that we need. The real 3 equations, okay? Put a pin on it because you're gonna need these equations to further solve the exercises, okay? Remember that you need these equations in order to do that. The next slide, as you can see, sorry. Okay, the next slide is just the same calculations I just did, okay, and you can go through them because I just did it in my previous calculations. I just wanted to show you. Take a look at this drawing right here. I have Vf and Bg, and I'm looking for my V average. My V average will always depend on the amount of gas and vapor that I have related to the total mass of the substance. And then with that equation, I can easily calculate it with this. The way the book explained it is just a mathematical way, okay? I always try to relate those mathematical equations with my own experience in order to make it easier for you. But again, like I said, you need to read on your own in order to understand this. Okay, just recapping a little bit, let's just go through the stage. So how do I get data from this stage? So we were talking about the compressed liquid, but superheated vapor. Compared to superheated vapor is characterized by, in the region to the right of the saturated vapor line and the temperatures above the critical point temperature, a substance exists in superheated vapor. Guys, this is a lot of information, but at the end what matters of the information is that you actually take what you need, and you only have to take, if I'm honest with you, is this word, the superheated vapor. In this stage, which is here, you're going to have only vapor, okay, and that vapor will exist at some temperatures and pressures, and you need to find that information on a table for superheated vapor. Okay, that's all you need. I'm not sure, but I think I included a video about how the tables will look like. Okay, when you read the book will take you into the page number of the tables. Okay, at the end of your book, if you have the ebook, it's the same thing. At the end of the book, you're going to have a table with different properties. So we have a property for table for superheated vapor. For compressed liquid, it's simple, guys. Why is that simple? Because we have a table for compressed liquid, okay? But the compressed liquid, pretty much the compressed liquid properties depend on temperature much strongly than they do on the pressure. So when you have my TU or my TB or my TH diagram, you can approximate the values to the mixture tables. How so? Well, let's say you have some properties, and remember the state postule, you need pressure and temperature. Let's say you're given with temperature and pressure to define state number 1. Okay? What you're gonna do some calculations in order to define whether you are in the state number 1, whether you are a compressed liquid or not. But let's say you find out that you are in compressed liquid, like this. Okay, cool. Do I have to go into the compressed liquid tables? No, I will go into the mixture tables in order to find my GF, my YF value. Okay, in this case, you can get into those tables and approximate. For example, if you're looking for specific volume, you can approximate this value to a specific volume of the fluid. Or if you're looking for enthalpy, you can approximate your value to enthalpy F. Or if you're looking for internal energy, you can approximate this value to UF. Okay, so pretty much, even though we have a compressed liquid table, you're not going to get into the table. Just go into the mixture table and grab your value that refers to BF, HF, or UF. How so? Well, let's go back. This is a table. This is a mixture table. You have, for V, you have BF and BG. For U, you have UF and UG. For H, you have HF and HG. So what you're gonna do when you're in compressed liquid, just go into this table and grab this value. Okay, at a given temperature and pressure for sure, in order to fully define your state. Okay, so compressed liquid is the easiest of all states. Like I said, you can approximate those values to BF, UF, and HF. So, same thing. So this is what you have at 500 kPa. You have a saturated temperature of 151.83. But your point, it's 500, right, times, and also 75 Celsius. So if this is your saturation temperature and you heat this guy right here, that means that you are in compressed liquid phase. If you're in compressed liquid and you're looking for U, you can just take UF at a 75 Celsius and then find the value that you need. Okay? So, we're almost done with the chapter, guys. We have something that is called ideal gases. The tables that we have in the back of the book, they're meant to be only for water, for refrigerant, and some other substances, okay? But when we have gases, there's no tables developed for this. And gases, they need to be treated with an equation that is called the ideal gas equation of a state. An equation of a state, pretty much, any equation of the state, it's the one that relates pressure, temperature, and a specific volume of a substance. The simplest and best known equation of a state for gas substances is the ideal gas equation of a state. This equation predicts the PVT behavior of a gas quite accurately within some property selected region. Okay? So, let me just recap a little bit. When we are using or when we are required to study water, refrigerant, or things like that, then you get into the tables. When you are working with ideal gases and you need to use this equation, which is a lot easier than getting into the tables. What is the equation? The equation is pretty much PV equals RT. Okay? And this is pressure, specific volume, the R, which is the constant, the ideal gas, the constant gas, or the gas content, and then the temperature at a given position. Okay, we know that a specific volume is V over mass. So if I plug this into the equation, I get that PV is equals to MRT. Okay, this is the other equation. It's the same one. I'm just, simplifying my equation. This value can be found on the book. There is a table for these values, so you don't need to calculate or the molar mass. Don't worry about that right now because this is a lot of information, okay? So you don't need this right now for thermo. Just go and grab your R value so you can get it defined. And don't worry, you're gonna get later in the chapter, we're gonna have more time to talk and work with these universal gas constant and the molar mass and things like that. So if you go to this table, you're going to find the substance, and for each one of these air, helium, argon, nitrogen, and you have a lot of different ones, you're going to have a value for R. Okay, the unit for R is kilojoules per kilograms Kelvin. So there is something that is called compressibility factor, and I'm just including this as a matter of I want to say as a matter of information, informative. That's the word I was looking for. It's a factor that accounts for the deviation of real gases from ideal gas behavior at a given temperature. Like I told you in chapter number 2, in engineering, we study the ideal cases so we can adapt that then to the real cases. So when we are dealing with ideal gases, this is not an exception. There is something that is called the compressibility factor Z, and this factor pretty much accounts for the deviation of the real gases from ideal gas behavior. See, it's pretty much, so we had before PV, it's equals to RT. So now we're going to call about PV equals to ZRT. Okay, and this compressibility factor is the one that I'm telling you. So you're going to solve for Z, and we get that Z it's equals to PV over RT. Okay, with that value you can get pretty much more information about your state. C will be equals to 1 for ideal gases, because if Z is equal to 1, that will bring me to this equation again, and that's for ideal gases. Okay, and if C it's more than 1 or less than 1, then that will be another case. Okay, so there's another information that you can get from Z, and actually if you get a value of the actual the specific volume, for example, and then you get your compressibility factor, then you can get this value as well, and you can play around with those equations in order to find something. As far as thermodynamic goes, we don't deal with this pretty much. We only deal with the equation I gave you before, which is ideal gases.
And that will be all for chapter number 3. Thank you guys for your attention. Just remember that you need to read the book. I'm giving you a little guidance through the video, but you need to go through my resume content, the videos that I posted on Blackboard, along with my notes and presentation, and all of that combined will help you to understand chapter number 3 in a better way. So if you have more specific questions, feel free to reach out to me, and thank you very much for watching.